Figures created with fractal theory. Have you ever looked closely at a snowflake? If we magnify a small part of it, we can find figures that resemble the whole. This feature is called self-similarity. Another important feature is repetition, where the same rule repeats over and over. When these two features come together, we get fractals. Simple rules repeat endlessly to create surprisingly complex figures. Some famous fractal figures include the Koch curve, the Koch snowflake, the Sierpinski gasket, the Sierpinski carpet, and the Menger sponge. These figures may look very complicated, but the ideas behind them are surprisingly simple. They are created through repeated processes of adding and removing parts. Let us begin with the Koch curve. First, we draw a line segment and divide it into 3 equal parts. Then, we replace the middle section with 2 lines that form a small triangle. After that, we repeat the same process again and again. At first, it is just a simple line, but it gradually becomes more jagged and complex. If this process continues forever, the curve becomes infinitely long. Surprisingly, however, the Koch snowflake never grows outside the original circle around it. In other words, its perimeter grows endlessly, while its area remains within a limited space. Now let us think about the opposite process, removing parts instead of adding them. The Sierpinski gasket begins with a solid triangle. We remove the triangle in the center, then repeat the same process with the remaining parts. As more triangles disappear, a unique motif begins to appear. If we continue removing parts forever, the area becomes smaller and smaller, eventually approaching 0. Yet the perimeter keeps growing without end. The Sierpinski carpet works in a similar way. We divide a square into 9 smaller squares and remove the center square. Then, we repeat the same process over and over again. More and more empty spaces appear, but the overall figure remains the same. Things become even more surprising when we move into 3 dimensions. The Menger sponge begins with a cube. It is created by repeatedly removing the center and the middle parts of each face. As this process continues, the volume gradually shrinks until it approaches 0, while the surface area grows endlessly larger. The inside becomes emptier and emptier, while the surface becomes more and more complex. Fractal figures challenge many of the ideas we usually have about geometry. Most ordinary figures have whole number dimensions, such as 1-dimensional lines, 2-dimensional squares, or 3-dimensional cubes. Fractal figures, however, often exist somewhere between these dimensions. That is why fractals are so useful for describing the complicated structures we see in nature. Another fascinating example is the Cantor set. If we continue removing the middle part of a line segment again and again, the total length eventually approaches 0. Yet infinitely many points still remain. Does it not feel strange that something can have no length but still contain infinitely many points? Finally, let us think about the Mandelbrot set. By repeating a very simple rule of squaring a number and adding it again, we can create amazingly complex and beautiful figures. Even when we zoom in, similar patterns continue to appear. This figure shows the features of fractals especially well. When we think about it this way, fractals are like endless stories created from simple rules. Would you like to create your own fractal by choosing a simple rule?